All right, today I'm going to be talking about Marcus theory. Um, now, we want a theory that can describe charge transfer mathematically in terms of rate. So basically, we want to find the rate at which that occurs, and if it's favorable at all. That can be expressed in terms of the probability, as the difference in the probability of finding the charge at the acceptor versus 2 points in time. So this is like a discrete step in time. So what does Marcus theory actually say about charge transfer? It says that the energy offset, the delta G naught, is important in determining this rate. Also the reorganization energy, the initial momentum, which factors into the kinetic energy, the driving force, and it also can be expressed thermodynamically as that. And also the energy gap Hamiltonian. I'll be focusing on the delta G naught, or the offset energy, here. So all of these go into the Marcus equation, and with this we can kind of draw a curve. That's not what that picture is, but that kind of represents two Marcus parabolas. So those are different potentials that are represented by the parabolas. Those are drawn by the equation for potential energy. So here is the ideal Marcus behavior. And so this is simply generated by plotting what is an analog of the Marcus equation in MATLAB. This doesn't actually experimentally determine anything. This gives us kind of a theoretical understanding of what the rate, how the rate should change as we change the offset energy, or the energy offset. So here's the mathematical basis. So we want to define our initial state vector. That's the thing on the left. And we want to define it by being composed of of wave functions, and with the application of its relative states. We apply time evolution to this, and we can get this as the linear combination of those. And basically, through what we learned about probability and then probability density, this and this expression can be used mathematically and in application in MATLAB to determine the individual probabilities of the state being occupied by charge. So that can tell us the rate through the equation that I mentioned earlier. Here's a short movie. How do I play it?
Sorry, escape.
Escape.
And then go.
Right. So here's essentially what a sample simulation looks like. You see those two Marcus parabolas, the potentials, and there's a transfer of energy, as you can see, by the kind of propagation of a visible wave packet in the red region. And here are the results that I got after choosing about 20 points that I'm going to be talking about between 0 and 0.1. It's the points where we expect the rate to change the most. Instead of following the ideal Marcus behavior, I got kind of a jagged, periodic-looking results. It looks like broken glass. So I got to wondering, what could have caused the massive deviation from the expected and the periodic nature? So the periodic nature was most likely due to the wave packets corresponding to different eigenstates in either potential aligning and de-aligning. When they align, there's resonance and energy transfer, charge transfer becomes very efficient. That's what you see. They're going up and down because obviously they're moving over one another. So also the nature of how we calculate the rate of charge transfer in MATLAB is that we want to find the individual slopes of x. That's essentially what that rate equation factoring probability is. It's calculating the slope at each different or individual point. And so that's within a certain time step or a certain discrete step. As that gets infinitesimally small, it becomes a better and better representation. As you know, we can't just take 4 slopes of that entire curve and say, oh yeah, we can just average these out to get a good approximation of the average slope. Also, picking more points between 0 and 0.1 might give us a better actual picture of what's going on in this region. Might help us see the true nature of what it looks like within that region if we pick maybe 1,000 points. So yeah, although the simulations didn't entirely fit the model, it still provides kind of a rough representation of how we would expect the rate of change as delta G naught does. Because of how the slopes were taken, the accuracy may have suffered substantially. In the future, more points in the observed range could potentially give us more information about what's actually going on within that region. Another interesting future study would be pick energy offset values at which the wave functions align specifically, and you could thoroughly scan the area around the region where they align, as in like you could see how the rate would change specifically in alignment. That could explain the turbulence. Questions?
Okay, please join me thanking Adam, and his presentation is open for discussion.
Anyone wants to ask questions online? If yes, please speak to the microphone because we do not see the chat line. Okay, anyone in the class? You can say without question, like, I really like what speaker is given because, and it's also very accepted. So briefly, 3 questions. Why your figure is non-symmetric in respect to 0? Rate.
Which rate?
Both expected and computed.
Oh, why is it non-symmetric with respect to 0?
Yes.
Oh,
Yeah.
like how it's offset.
It shifted to the positive instead of negative.
Yeah. I would suppose in the calculation in the Marcus equation, this offset would kind of be determined by the solvent reorganization energy. Maybe it would be contributed to the specific offset, whether it be I think positive or negative may affect that as well.
Okay, so nothing is wrong, but not
Fully complete, but good. Then the question number 3: what is activation energy? Wait, right on the slide where you were.
Oh, this one. The activation energy?
Yes.
Okay, so that would be noted by delta G double dagger, and basically what that is it's the distance between here. It can be measured. It's essentially going to be, I think, the square of the sum of the solvent reorganization energy and the offset energy, the square of that over 4 times the solvent reorganization energy. So that's how it's mathematically.
When this activation energy is 0, when it is minimalistic, for positive or negative offset?
It would be when the activation energy is 0. It would look right here. So it'd be a negative offset. So
but it is unsymmetric, right?
Yes.
If you swap, then it will be substantially changed. So it is answer on the first question.
Yeah.
Okay, and the last one: if you keep the same offset and reorganization, but change frequency like 10 times smaller, how will your results change?
The frequency, as in the driving kinetic energy, so the excitation or the driving force.
Vibrational frequency. Let's go to your eigenstate.
Yeah.
Or your next. Yes, sure. If the vibrational states will be much more sparser, if it is like not 0.1 or 2 volts from each other, but really, really dense.
Could you point out what you mean?
Yes. If the offset in energies between like prone and excited, you'd be like 10 times smaller.
Oh,
This figure would change.
yes. Yeah. So that would maybe we'd see actually more alignment with the expected curve
Excellent.
if we did that. Because
Yeah, that's correct. More questions to Adam?
1, 2, 3. If no, let's thank Adam once again.